Hello all of you. I am Richa Sharma from Geosciences and Geohazard Department IRS. Today I am briefing you about the hyperspectral data analysis for the geological applications. First of all, now we'll see what exactly we mean by the hyperspectral remote sensing. The hyperspectral remote sensing, what we say, is the science of acquiring digital imagery of the earth materials in many, narrow and contiguous spectral bands. For the hyperspectral analysis, two things are very necessary. Number of bands more, they should be continuous, or we should say it's contiguous, and they should be bandwidth of those will be very less, very narrow. And now, as we can see that the advancement in the solid state technology in the recent years, now we will be able to collect the hyperspectral data in as many as 200 or the more number of bands. For example, if we say about any airborne data, that is somehow Everest, the Everest we can collect around 224 bands. And if we take an example of a satellite data such as Hyperion, then around 242 bands, and out of them around 224 are the useful bands. Now, these bands, with the help of these many spectral bands, the spectral range, what we are going to cover is from 400 nanometer to 2500 nanometer. Now, first of all, let's see what exactly we mean by the spectral resolution. When we were dealing with the panchromatic data, only one band was available. Then, with the spectral data, now we'll be able to go for the few bands and we can generate the FCC. After that, with the help of the hyperspectral data, now we'll be able to generate a continuous spectrum of a material from 400 to 2500 nanometer or 400 to 1000 or 1100 nanometers. Now, as we can see in the previous slide also, as we can see here, in the panchromatic data, only one band is available. In multispectral, there are few bands, but those bands are not contiguous. We have taken few bands up to 1000 nanometer, after that from 1.5 something and then 2 onwards. So there is no contiguity in the data, but in the hyperspectral data, when we see, if we have started at 400 nanometer, we have to go till the 2500 nanometer with no band interval, with no band gap. Now, when we say for the conventional remoting, the differences, as we see, the narrowly defined spectral channels. First of all, the spectral channels are very narrow. Then they are, when we see about the multispectral, they are the broadly defined spectral regions. As we can see in this slide, the previous one is the example of a lens at TM. In that, we will be able to get only 5 or 6 points, and when we are seeing the imaging spectroradiometer data, we will be able to see the continuous spectrum. Now, if we look into the differences of the multispectral and the hyperspectral images, now we can see that help of multispectral instrument, we can discriminate the minerals, as well as when we go for the hyperspectral data, we will be able to see or actually identify the mineral which is one level above the discrimination. Then, if we go for the multispectral data, then we can detect the existence of various materials, same as we can discriminate with the multispectral we can detect, and then we can detect, and with the hyperspectral we can identify, and the same thing we can identify, or the identification of the material is possible. But the other thing is multispectral, the accessibility is greater, whereas when we say about the hyperspectral sensors, most of the hyperspectral sensors are the airborne, so the availability or the accessibility of the data is a very big question with respect to the Indian scenario, because we as a personnel, we don't have any typical Indian sensor. So when we go for the airborne data, then the flight scheduling and the coverage area and the airborne hyperspectral imaging is a big challenge for us. Now, but the Hyperion data, spaceborne data, what we have for the hyperspectral is the Hyperion, and that is freely available, can be used by the Indian. Now, again, the comparison, we can see that with the help of lens at TM, now these 6 points we will be able to generate with the MODIS, because it has the 8 band data, so 8 bands we can generate, and with the hyperspectral, the average data, the continuous spectrum can be generated. Now, if you look into this figure very carefully, when you see for the first spectra that has been generated from the Landsat TM for the same mineral illite, you can see in the description also that the 6-band Landsat TM data set shows the 6 data points concentrated on the different 6 bands, and for the MODIS there are the 8 bands of the MODIS data. So we will have the 8 different points and it will give you the different curve. But by seeing the Landsat, the spectra generated by the Landsat or the MODIS, and when we compare these two spectra with the hyperspectral spectra, now you can easily understand that both the spectra look similar, but general trend is same. But in between there are different absorption dips. Those we won't be able to see using MODIS or Landsat data. Values at 1.4 and 1.5, you can see over here 1.4 and 1.5 values are very peculiar features for the illonite mineral, and those are not in this or the Landsat data, whereas with the hyperspectral data these can be seen very nicely. Now, as this 5th point says, wide spectral bands could not find the feature, and the TM and MODIS samples do not even have the bands centered on these wavelengths. See, because the spatial peculiar, what I said you before also, the absorption dip is at 1.4. These bands which centered at 1.4 or 1.5 is not available either in MODIS or in Landsat. So we won't be able to see that particular dip which characterize the mineral illonite. So we conclude that the hyperspectral remote sensing, with the help of this, we'll be able to generate good quality spectra, and with those spectra we will be able to identify exact material using their characteristic absorption dips. Now, as far as we say about the visualization of the hyperspectral images, we sometimes say them, we call as image cubes, because they have large number of pins, and so the X and Y directions are it shows the spatial information, and the Z direction will show us the spectral information for that particular pixel. And when we generate the XY plane, that may be any FCC or any composite from any 3 of the bands. And then we use it as the RGB. Maybe true color, maybe FCC or whatever we require. So the number of bands or the band combination we can gain accordingly for generating our first XY plane. And the Z direction will vary according to the number of bands present in that particular data. Say 100, 150 or maybe 200 or 250. How many bands are there in that particular data? Bands will be represented in the Z direction. Now these bands are summed together, and then we will be able to create a continuous spectra. For each pixel, we will be able to generate a spectra that will denote the properties of that particular pixel from band number 1 to band number 250 or 224 or whatever is the wavelength chunk. Now you can see in this example, this is the photograph or the hyperspectral image of different fruits, and now with the help of this, say this particular part, if we generate the spectra of any pixel of this area, this orange pixel will give us the spectra like this in this pixel, and when we move the spectrum, what we are getting over here is because of the reading of this pixel in this Z direction. And if we say for this, if we see this is also for this particular pixel in all the bands, whatever bands available in this data. Same for the black grape also, it is there, and the other things, what are the fruits available in this, green grapes and everything. And if you observe fully, you can see that the spectra of each fruit, what we are collecting over here, is different from the other. So if we know the exact spectra of that particular material, we can identify it by seeing their spectra. Now this is the example of a hyperspectral cube, or we can say hypercube of the Jasper Ridge, California. And in this cube, we can say that the X and Y axis are representing the spatial data, and the three band composite what we will be able to see over here are for the band number 43, 7 and 10. These three are the RGB component. So red color is assigned to the band number 43, green color is assigned to band number 70, and blue color has been assigned to the band number 10. So with the help, by assigning these three, the FCC what we are getting is over here. So this XY plane shows the FCC which is generated by these three band combinations, and direction are the number of bands available. And this is the number of bands over here are the 224, and they cover the range from 0.4 to 2.5. This is nanometer, nm. Now, as you must have heard that the hyperspectral remote sensing is also known as the imaging spectrometry. Now, why do we call it as the imaging spectrometry? First of all, we have to understand what do we exactly mean by the spectrometry. In general word, we can say that the spectrometry is the science in which we study the interaction of the matter and the radiant energy. And the spectroscopic data what is represented by the spectrum, and this is the plot which is the response of the interest, and compared to is the function of the either wavelength or the frequency. Now, when we say this hyperspectral remote sensing as the imaging spectrometry, because with the help of spectrometry we are able to generate the spectrum, and with the help of the spectrum we can see the data. With the help of the spectrum we can identify the material. And when we see about the imaging spectrometry, with the help of the image, the spectrometry of the spectroscopy of that particular area can be done. So the hyperspectral remote sensing is known as the imaging spectrometry or imaging spectroscopy. So in the definition we can say that the imaging spectroscopy of the remote sensing involves the acquisition of the image data in many contiguous. You have to look into this word contiguous, because whenever we are talking about a hyperspectral data, the contiguity is must. So it is the acquisition of the image data in many contiguous spectral bands with an ultimate goal of producing laboratory quality reflectance spectra for each and every pixels. So we have to create a spectra or the reflectance spectra for each and every pixel, so that this spectra can be compared with the laboratory spectra. So the mapping of that particular material can be done by matching with this spectra generated through the image to the spectra generated in the laboratory. Now you can see that this is what I was telling you is the imaging spectrometry. See, this is the hyperspectral image for an example, and we have generated the spectra of each and every material available on the spectrum. For example, we have taken only 3. First is for the soil. So we have selected a pixel which represents soil class, and the spectrum of that particular soil class has been generated. This axis says the number of bands or the wavelength ranges from which it started, and this is the z-axis for that, and the vegetation, this is the vegetation, and we have the spectra of the vegetation. Then third, there is a water, and this is the spectra of the water. So as the spectrometry, with the help of the hyperspectral remote sensing, as the spectrometry we can generate the spectra, and with the help of we have already done with the spectrometry calculation of the spectra. By seeing the spectra we can identify the material. The identifying of the material can be done using the hyperspectral remote sensing. Now the question arises, why do we use the hyperspectral remote sensing, or what is the advantage of the hyperspectral remote sensing for the geological application? Now to understand this question, that why do we need hyperspectral remote sensing, or why hyperspectral remote sensing has been used now? So we have to have the basic knowledge of the spectroscopy. because right now we have the sensors from 0.4 to 0.4 to 2.5 micrometer region. First of all, we'll study the spectroscopy in this region only for 0.4 to 2.5 micrometer. Now we can see over here, there are the different curves we get in that particular range, 0.4 to 2.5, and each spectra, whatever spectra we have seen over, we can see on our slides, each spectra represent a particular type of a material. See, the green says about the vegetation. Whatever vegetation is there, whenever we will get the vegetation cover, the spectra will more or less look like this. Only differences will be there. There will be change in the intensity of the reflection, but the values, the reflectance will be high in the IR region, and there will be absorption at 1.4 because of the water content, and around 1.9 because of the water content in the green leaves. This spectra what we are getting because of the good quality chlorophyll, present chlorophyll in that particular vegetation. Then there are the different spectra of the soil. Because of the soil, the spectrum will be, the reflectance will be high, and the wet soil, the reflectance will be low. And we can see over here, the whatever peak, because it contains 5% of water and it contains 20% of water, the dip is more in this 20% of water, because at 1.9, whenever we are getting absorption dip, that is a typical dip of the water. So when the water content is less, this dip, whatever we are getting over here at 1.4 and 1.9 is less, the depth is less, and it is more when the water content is more. Now we should see these things for the mineral content. The first spectrum what we can see is the spectrum of a calcite material. In this calcite, because of the presence of the CO3, there is a peculiar absorption dip that we will be able to see at 2.3. Then there is the other mineral, the clay mineral, what we call is it as a kaolinite. The kaolinite will give us the double, we can say doublet of absorption. The doublet absorption is at 1.4 and 2.2. You can see a doublet. The dip is not just a single dip, it is a small dip and the other one. So this doublet at 2.2 is very, very peculiar for the kaolinite mineral. Then there is the other mineral, clay mineral, montmorillonite, that we can see over here. Dip as 1.9 and 1.4 because it may contain some water, and the doublet says that it is the montmorillonite at 1.4. Now when we see about the hematite or the iron mineral, the iron mineral will have a broad dip between 1.9 and between 0.91 micrometers. You can see over here. This is typical for any iron mineral. Now, so in reading the spectral curve for this information content, the most useful feature what we have seen over here is we can see spectrum, we can see the reflectance everywhere, but these absorption dips, what I am telling you is, for example, a 2.2 dip for kaolinite, or this 0.9 and 1 micrometer dip for iron is important. So what we have to analyze is, we have to analyze the location and depth of the diagnostic absorption bands. Now, these absorptions are caused because of the, we can say there are three different types of absorptions. First of all is the charge transfer absorptions, then electron transition absorption, and vibrational absorption. Now let's first discuss about the charge transfer absorptions. These mostly occur in the visible region of the spectrum, and they are caused by light at certain wavelengths, causing the electron to be transferred between the atoms. The example is Fe3 plus and Fe2 plus. When a particular wavelength of light has been incident on this, the electron is transferred from Fe2 plus atom to Fe3 plus atom. This is because of the charge transfer absorption. You can see over here the spectra of some minerals, which shows the charge transfer absorption in this at this particular point, as I have already told you, near in visible region. These are the things we can see over here, and these absorptions are very broad. In general, this type of absorption is quite broad, hence it would be possible to detect them in the conventional multispectral techniques such as lens head, but whenever we are getting the same absorptions for three different minerals, then those will look similar in the multispectral data, but when we see them into the hyperspectral data, then we can exactly pinpoint them. Now, the second kind of absorption, what we say, is electron transition absorption, and in this, the atom with a complete electron shell, when the light is incident on that particular wavelength, it will bump into the different positions in that particular cell. So these absorptions tend to be narrower, they are narrower than the charge transfer absorptions, and the wavelength of the absorptions are controlled not only by the type of atom but also the position and the variety of its neighbors. So this feature is especially useful in geology. So what we say that among these three different types of absorption, the electron transition absorptions are important for the geology, and because when the arrangement of the atom mineral is very well defined always, and whenever there is a small change in the arrangement because of the neighbors also the absorption changes. So the subtle variation in the position of the bands are very important, and therefore we need a very narrowly spaced bands so that we can take full advantage of this in future. Now, third are the vibrational absorptions, and when the light at the same wavelength as a module, as a molecule strikes the molecule, it causes the molecule to vibrate. When the wavelength is the same, then it causes the molecules to vibrate, and because those vibrations, there are absorption in the light. And in general, these absorptions are very narrow, and although their widths and depth vary accordingly. Of the absorption seen in the 0.4 to 2.5 micrometer region actually originate at the longer wavelength, but what we will be able to see over here are the combinations or the overtones of the original wavelength. And most of these absorptions can be detected with the hyperspectral sensors. Now, as we see for the geological applications, because of the unique spectral characteristics of the many alteration in the rock forming minerals, the hyperspectral remote sensing is making a significant contribution to the field of exploration geology. And with the help of this hyperspectral remote sensing, we will be able to distinguish the spectral features of the different minerals that can be seen in the short-wave infrared region due to the bending or the stretching features of OH, CO3, Al2 plus and OH bond, Mg and MgOH bonds, SO2, and different other bonds which are present in the minerals in the short-wave infrared that can be seen in the short-wave infrared region. Now, the next thing is the hyperspectral processing. As I have already told you in this, that there are some standard hyperspectral processing techniques that we have to use for the processing of a spectral data. There are different hyperspectral sensors of the hyperspectral data we can always have. Most of the data are airborne, as I have already told you, like Everest, Kasi, etc. And the hyperspectral data that is space-borne we are getting is the Hyperion, and that Hyperion, the standard process what we have to go for the hyperspectral particular Hyperion data to get the spectrum is already identified, and we have to go through the same steps. See, as we have already seen in the multispectral data, that multispectral data, whatever bands we have selected, for that we consider for the atmospheric windows. So we collect the data among those wavelength regions where the effect of atmosphere is minimum. But for the hyperspectral data, we cannot do that. We have to collect the data from a particular point to the particular point with no gaps. The contiguity should be there. So the atmospheric correction is the very important step for the hyperspectral processing. Therefore, first is the apparent reflectance that we have to calculate through the atmospheric correction models and techniques. Then, sorry. Then, because the hyperspectral data has the large amount of the data, so the data reduction of the data is very important. Those data reduction techniques are used to reduce the number of spectral band, but they should contain the maximum number of information that is present in that particular data. So, for example, if we have 220 bands in a data, so with the help of spectral data reduction techniques, we will try to reduce the number of bands, but the number of information or maximum number of variants should be there in the, say, after performing the data reduction techniques, if we have selected 10 bands or 15 bands, so number of bands are less, but the information is may 90%, 99% or 98% of the whole data. So very less information is lost, or maximum thing what we have reduced is the noise content or the coherency in the data. Then after the spectral data reduction, the next step is the spatial data reduction of the image. So with the help of first, with the help of the apparent reflectance, we have removed the effect of atmosphere. Then with the spectral data reduction, we remove the noise and we have reduced the dimensionality of the data, so that for less number of bands, the information of all the bands are there. And the third step is the PPI, that is the spatial data reduction. For that spatial data reduction, we will try to identify pixels which are pure, so that we can identify, we can concentrate on those pixels only, that so that we'll be able to identify those Endmembers, or those we have to concentrate on only those pixels which have the probability of being a pure pixel is very, very high. And whenever we by the spatial data reduction techniques, or what we say, the pixel purity index or the PPI, when we will be able to generate a PPI image in which we are getting few number of pixels, those pixels are the purest pixels. Only those pure pixels we will visualize using the n dimension visualizer, and then those pixels we'll try to identify them for that particular class, say for water class or for soil class or for a particular mineral, and that particular pixel or a set of 10-15 pixel will be given as the training set for the classification of the whole image, and then that classification algorithms will be applied. The classification algorithms used in the hyperspectral data are slightly different. They are SAM, MTMF, SFF, and on. And with by applying these data techniques, for the classification, you see the mineral abundance map or the distribution maps. Now let me show you some case studies that with the help of them you will be able to understand exactly how we are doing the processing of the data. The first study what I am telling you is for the Udaipur area, that is in Rajasthan, India. First, whenever we get these studies, what I am telling you is on we have applied on the Hyperion data. This data is freely available, and we can download it from the USGS websites. Now, whatever data we have, it's level 1, we corrected data. This level 1 corrected data, what we have to do, there are still some errors in the data. For example, you can see that there is a stripe in the data. The values of this particular column, bad column, is 0, 0, 0. Then what we have to do, we have to average these column pixels with the neighboring two columns so that the value, this striping error will be gone. So when before de-striping there is a stripe in this image, and when we applied this de-striping, the that bad column has been removed. Now when we look at Hyperion data, there are few bands in which no data is there. So those bands we call it as the bad bands, and those bad bands we have to remove. We have to subset those bad bands. So with the NV software, there are some methods, there is some options. With the help of them, we can subset a hyperspectral data spectrally, so that the spectral bands which are not of our use can be removed, or specially so that whatever is our area of interest can be used. So for this study, we have used the following bands. Band number 1 to 7 for all the Hyperion data. Band number 1 to 7 is not useful. It contains no information. It is completely black. And some bands, as we have seen from 57 to 78, 58 to 78, these bands are either completely black or complete white. So they don't contain any information. They are completely black or completely white. So we have to remove those bands. So we have subsetted spectrally. We have selected band from band number 8 to 57. Then in SWIR range, we selected from band number 79 to 164, and like that. So the total number of bands, or total number of calibrated bands what we have got are 145 in number. Now, as I have already told you, the first step what I have told you was the correction of the atmosphere for the Hyperion data. And the steps what I have shown you is the removal of the bad columns and bad bands are the pre-processing steps. So they have to be done before the atmospheric correction. And after this, we have to do the atmospheric correction. See, the image what we get is the radiance image. And this radiance image, we have to convert it into the reflectance image, because whatever spectra we have seen till now are the reflectance spectra, and we have to map these spectra with the ideal library, and that ideal library has the reflectance spectra. So that reflectance spectra has to be this radiance image has to be converted into a reflectance image, and for the conversion we have to use different atmospheric correction algorithms. And here in this slide, for this study, I have used the flash algorithm. This flash algorithm is available in NV form. And before flash, the spectra of a vegetation, that is very common spectra, you can see over here, the spectrum of this particular pixel in this before atmospheric correction is look like this. Whereas when we have applied the atmospheric correction, the same spectra for the same pixel has been corrected, and now it has it is the reflectance spectra of a vegetation. It is more or less similar. As we have seen in the vegetation also, it will have there will be a dip in the visible, and there will be a peak in infrared region, and after that there will be a dip around 1400. Then so we will be able to see the exactly same spectra of the vegetation after using the atmospheric correction algorithm. Now, the second step after atmospheric correction was the selection of the Endmembers. So, for the selection of the Endmembers, there are different things we have to apply, and those different things are because the Endmembers have to be selected carefully so that they will note only the pure pixels. So, those pure pixels, how do we do that? First of all, the MNF we have applied, that is called the minimum noise fraction. So that minimum noise fraction will give us the images, some maybe, for example, if we have given input for in input we have given 224 bands, then the software will give us 224 MNF bands. Out of those MNF bands, we have to select the MNF bands which has maximum number of eigenvalues. and the bands which have the eigenvalues of near unity or around 1, those bands will contain only noise, so we don't have to choose them. So whenever we see the plot of MNF, then whenever we are getting this, that MNF plot is constant, then only those bands where we are getting that notch have to be selected. Say for example 10 bands or 15 bands maximum. So we have selected those bands, and those 10 bands are used as the input for PPI, pixel purity index. So those 10 bands what I have selected, I have given the input to the PPI. So we will get a PPI image, that is a black and white image. In that PPI, the pixels which are appearing pure will appear white, and those pixels which have not appeared pure pixel even a single time will appear black. So the pixel, so all the pixels or any pixel which is appearing white in the image will was recorded pure pixel maybe once, twice, thrice, or maybe in number of times. So whenever we see the location value of every pixel, so the DL value of a PPI image will tell us how many times that particular pixel is recorded as extreme. If it is appearing white, it means that pixels has appeared pure, and if it is black, it means that pixel has not appeared as a pure pixel, or it was not marked as pure pixel even once. This selection of this pure pixels, how it is doing, the software is plotting all the pixels randomly between two bands, band B1, B2, or like that. So whatever pixel is appearing at the corners, for example, if this is a scatter plot and this is between two bands, so this is the cloud of these are all the pixels which are plotted over here. So the pixels which are at the extreme corners, these are the pixels which are the part of the clouds. These pixels are the pure pixels for this particular class. Right now, the software is not assigning any class. That class will be assigned by us after seeing the spectrum and matching the spectrum with the library, or matching the spectra of the particular point which we have collected from the field. Right now, the software is giving only the location of the pure pixels. So, for example, these 4, 5, 7 pixels are appeared as the pure pixels, and these pixels are located at this position. This will show the position of the pure pixels in the scatter plot, and PPI will show the position of the pure pixels in the XY location. Now, whatever pixels we have selected as pure pixels, say 10, 20 or whatever, say for this particular class, 5 from this place, 2 from this place, 3 from this place, like that. So we have to plot these things randomly, twice, thrice, and number of times, and for each time some pixels will be appearing, some pixel will appear as the pure pixel, and only these pixels we will select them for the end members, and then we will generate the spectra of these pixels. Say for example, we have selected pixels and we have generated the spectra of that pixel. So the red line is the spectra what we have generated from the image. Then there is a black line. This spectrum has been generated from the library as well as the field. So whatever spectra we have generated from the image, that spectra we have matched with the ideal spectral library that is available in, and it is there are 3-4 types of library available in NVPR. USGS spectral library, then there is JPL library and JHU library. So this I have matched with the USGS library, and when we matched using that matching has been done using the tool spectral analysis. So when we have matched this spectrum, what we have generated from the image with the spectral library that is there in the spectral library that has already been given into the different different USGS or other parts, then this will give us the score of that particular spectrum with respect to that particular ideal laboratory spectrum. So whenever the score is high, say 80% or 90% or so, whenever the spectra which we have generated already from the image is matching more than 80% with the spectrum that they have generated from the library, or the spectrum that we have collected from the field, then we will assign that particular spectrum at that particular class. So now, for example, over here we can see that these are the spectrum what we have collected. So these see that these are the spectra of montmorillonite. This is a clay mineral, and we can see over here the dips are the peculiar for these two spectrum, and the general trend of the spectrum is also similar, so we can match them. And when we have run the algorithm spectral analyst for this is the image spectra to match it with the USGS library spectrum, then it has given us the score of this, the final score. So this percent means 90%. The spectrum is matching with the USGS ideal library spectrum. It is 90% match. Now this is for the another mineral dolomite, and this is for the goethite. As I have already told you that goethite, this is the typical absorption what we are getting for the iron minerals. So this is the dip we are getting in these three. There is a slight shift in it. The field and the USGS spectrum what we are getting is they are matching very perfectly, and the match is I think more than 70-75% or so. So we have assigned this spectrum as the spectra of that particular goethite. Now this is the final image. We have classified this image into these many classes, and whatever distribution of the minerals we are getting in our whole strip of the Hyperion is this. So we will be able to identify these classes, montmorillonite, illite, goethite, dolomite, and all these things. Now these are the steps what we have to follow for each and every classification of each and every scene of the Hyperion data. And this was the study for the Udaipur area, and there is another study that we have performed in the Rampura, Agucha and Nipur Banera area of the Rajasthan. Now you can see that these are the three different spectra what we have got from the field as well as the image, and the same procedure has been applied, same kind of corrections has been done, atmospheric correction, then we have applied data reduction techniques, then we have applied, then we have gone for the pixel purity index, we have identified the pure pixels, we have plotted those pure pixels into the scatter plot, and then we have generated the spectra for the selected Endmembers. Then we have matched those spectra with the spectrum of the library, and whatever spectra and which spectrums are giving good score with the library, as we have seen before, more than 75% or more than 80%, those only will be selected for the defining the class, and only those classes, those spectrum will be used as a training class to identify to map the whole image. So in this there are the three Endmembers we have selected: hematite, then pyrrhotite, and montmorillonite. These are the three minerals. Now hematite is so iron mineral. We can see this dip over here around 1000, and there are two other minerals, this clay minerals and pyrrhotite. And we can also say that these three, this one is the image spectra and the other one is the field spectra what we are getting. So these are the end members we have selected from the image, and with the help of these three spectra we have classified the Hyperion whole image into three classes: hematite, montmorillonite and pyrrhotite, and this is the classified image we are getting. The pyrrhotite we are getting over here, this area, and in this region we are getting a hematite, and this we have verified in the field also. In this area we are getting the boson samples for the iron, and this area, when we have collected the mine samples of this area, we will be able to generate the same, we will be able to identify the same mineral in the field samples what we have collected. Now the last example what I am showing you is the Hyperion images, E1 Hyperion image for the Nevada area, California. And this data, whatever data in this image, the left hand side image you are seeing, was acquired in on July 23rd, 2001. And the spatial resolution is around 30 meter, and the spectral resolution is around 10 nanometer. For the Hyperion, the spatial resolution what we get is 30 meter, and whatever spectral resolution we are getting is the 10 nanometer. So the left image is the true color composite image. It is a true color image, not FCC. It is true color composite of Hyperion bands, and bands what we have used is 31, 20, 10. And the right image is the mineral map using for shortwave bands in this range. We have used only 40 SWIR bands. Using only 40 SWIR bands, this classification has been done, and that has been overlapped on the image. So we can see different classes over here, some green and all the different colors: green, cyan, purple, red and blue. And these color denotes, green color is for the muscovite, then the blue, there are two kind of muscovites we will be able to identify, this green and blue. Then the red color is for the mineral calcite, the yellow color is for dolomite, purple color is for silica, whatever silica contents we are getting is there, and cyan color is for zeolites. So now we can conclude it something is like that: with the help of hyperspectral images, as we have seen in the case studies also, with the help of these Hyperion images or the other hyperspectral images, because of the presence of typical absorptions of the minerals present, we will be able to identify those minerals, those material easily, and we can pinpoint them properly, and we can know their distribution exactly. So as the traditional technique, as the traditional geologists who are doing the field works for months or so, and then they'll be able, then they can identify the area. Now with the help of hyperspectral imagery, we can identify the mineral deposits using imageries, and then we can go for the field truthing for 1, 2 or 3 areas. And this way the mineral prospecting has reached another direction, and the accessibility, when the area where the accessibility is not good, the inaccessible areas, the detection or mineral targeting can be done. So that's all for the lecture, the mapping of, or we can say the analysis of the hyperspectral data for the geological analysis.